Hello, hi. My name is Dan Daly. I'm a software architect at Intel, and it's my pleasure to introduce Ben Pfaff from VMware, who's going to talk to us today about P4 and Open vSwitch with OfP4. And I feel like Ben sort of doesn't really need an introduction. He is one of the lead developers on Open vSwitch, and as a big part of Open vSwitch is the way that it made OpenFlow, a part of the Linux kernel. And that work was started when he was working at Nicira, and now he's currently at VMware. He got his PhD from Stanford in 2007, and he has been working for over 20 years on open source and free projects, including Debian and GNU. So with that, Ben, let's start.
All right. Thanks, Dan. So today, like Dan said, I'm talking about OfP4, which is a software switch for P4 that my colleagues and I are prototyping in the research group at VMware. So let's jump right in. So first, let's motivate it. Why build a new P4 switch? We were motivated by the lack of a high-performance implementation of P4 in software. The popular BMV2 software switch is an accurate simulator, but it's not fast. We had trouble installing the academic Tapas switch outside of the exact distribution that its authors used. And the Pisces switch is unmaintained and it doesn't support P4 runtime. There are others in development too, but none of them is quite what we want. So we built our own switch, which we call OfP4. We didn't want to build a whole data plane of our own, so instead we decided to use Open vSwitch. That takes some explanation, and that's what this talk is. So let's start with how the system works. First, we take a controller that uses P4 runtime and a P4 program that it expects to control. Then we compile the P4 program with a compiler backend specific to OfP4. Then we plug the compiler's output into OfP4 and connect it to the controller using P4 runtime. Finally, we connect OfP4 to Open vSwitch. OfP4 then translates P4 and P4 runtime into OpenFlow and uses it to control Open vSwitch. The effect is that Open vSwitch then implements the P4 program. This uses regular unmodified Open vSwitch since OfP4 is just a daemon process. It does need Open vSwitch extensions to OpenFlow, so it won't work with other OpenFlow implementations. The P4 and OpenFlow architectures have a lot of differences, so we need to look at how we reconcile those. The OpenFlow switch architecture is just a single pipeline, which consists of several tables, each of which contains flows that have a ternary match, actions, and a priority. On the other hand, the portable switch architecture, or PSA, in P4 has two separate pipelines bracketed by a programmable parser and deparser. To make a P4 architecture more like OVS, we take the parsers and deparsers out of PSA, like this, and instead supply just the headers that Open vSwitch knows how to parse. But Open vSwitch is flexible enough that OfP4 can make it act like there's a pair of pipelines anyway. So OfP4 keeps this part of the architecture. We only have time to look at a couple of aspects of translating P4 to OpenFlow, starting with metadata. P4 architectures specify named standard metadata for every packet, and P4 programs can specify their own named program-specific metadata, like shown here. On the other hand, OpenFlow and OVS have a fixed number of metadata fields with fixed names. Some have assigned purposes, like import, and others are available for any use, like reg 0 through reg 15. OfP4 uses an allocator to map P4 metadata into OpenFlow metadata fields, or parts of them. So there's a few standard metadata fields that have direct equivalents, like import here. Other P4 standard metadata fields don't have equivalents, so OfP4 just picks generic OpenFlow metadata to map them to. And we can see that here for outgroup and outport that get mapped to different parts of reg 0 in this case. Program-specific metadata never has direct equivalents, so OfP4 always picks a generic OVS metadata field. And finally, OfP4 can use parts of OVS metadata fields for program-specific metadata too. OfP4 maps a P4 table into an OpenFlow table, and P4 table entries into OpenFlow flows. Let's look at how the key part of P4 table entries gets translated into OpenFlow matches. So first, exact match parts of a P4 table key end up as match fields in an OpenFlow flow, like a match on the ingress port becomes an OpenFlow match on the in port. P4 can match in arbitrary expressions, like on whether a header field is valid. OfP4 is smart enough to deal with this in simple cases. Like here, a match on whether there's a VLAN gets translated into in an OVS match on the VLAN present bit, either that is not present, like that one, or that it is present, like this one. P4 has a bunch of different match types. Most of them translate okay into OpenFlow's ternary matches. An optional match, like the one on VLAN vid here, can become no match at all in OpenFlow or an exact match on the vid bits in the OVS VLAN TCI field. OfP4 translates actions that a P4 table can have into OpenFlow. For example, this implementation of a drop action changes the standard metadata to indicate that the packet should be dropped and then jumps to the end of the pipeline. OfP4 happens to allocate reg3, so it translates into setting that field and then jumping or resubmitting to the end of the pipeline, which happens to be OpenFlow table 31 in this case. And then the equivalents of these other actions are also straightforward. So other parts of P4 need to be translated to OpenFlow also. This slide lists some of them, which we don't have time to go over. And there's a lot more details. You can find out about those in our repository in the OfP4 branch.
Great, thank you.
Thank you, Dan.
Yeah, this was great. Have you looked at a set of P4 programs that you wanted to target, or do you have a use case in mind that you're looking to use this for?
So what really motivated us here was that we're building a system for making control planes and data planes together, and we wanted to use P4 for the data plane part, and we wanted to use it for software, but we didn't have a P4 software switch that we really liked for production, so we're starting out building and prototyping this compiler with really simple programs, and that's the point we're at in the prototype. But eventually, we want to get to the point where we can run really sophisticated ones that that go up to, say, the level of network virtualization that VMware's NSX product or OVN or things like that can do. It's a pretty big lift. At the moment, it's a research project, so I don't know if we'll get there.
I see. Yeah, yeah. I think that would that mean then that potentially there could be a version of OVN that had P4 at the bottom of it instead of OpenFlow, or?
I think that would be super. I'd sort of like to look forward to that, but we only have a couple of people on this project, so our initial goal is to try to make something that works like OVN did in its very first release, which is much simpler than OVN as it currently sits.
I see. Okay. And have you been pretty happy with the performance that you're getting out of it? Is it similar? Do you lose any performance when you compare it to just regular OpenFlow inside of OVS?
So far I can really only speculate on the performance, but this
Okay.
is the sort of thing that OVS was built to support. I think that the OpenFlow flows we'll get out of this will be a lot like the ones that we get out of OVN or Faucet or other controllers. They might use a few extra tables, but that sort of thing is something that OVS is meant to handle gracefully. I think that OVS's caching and so on will tolerate the flows that we generate quite gracefully.
Okay. Cool. Excellent. Thank you.
Oh, you're welcome.